Okay, so let's continue with our discussion on gases. So far, what we've started thermodynamics by saying that we will look at both macroscopic description, mostly of gases, in describing gases in terms of their pressure, volume, temperature, and mass. We started by talking about the definition of temperature and how it affects an object. An object heated up will expand, for example. And then part of thermodynamics is looking at what's happening microscopically, what's happening to the atoms and molecules that's making up the objects. So in today's lecture on kinetic theory of gases, we will try to reconcile these two descriptions and see how the behavior of the individual atoms relate to the what we observe macroscopically, specifically in terms of temperature. So we will focus more on temperature today, but just to recap, yesterday we learned about the ideal gas laws relating the state variables, the macroscopic descriptions, pressure, volume, and temperature. And we've seen these relationships here, and I brought my demonstration because the rain has stopped. So Boyle's law says that assuming that the temperature of the gas is constant, then the volume should be inversely proportional to the pressure, meaning if you decrease the pressure, the volume should increase, and vice versa. If you increase the volume, the pressure, the volume should decrease. So I have here with me something that I can vacuumize. If you mind. So this is a vacuum pump that will suck up all the air inside this chamber, and I put the balloon here and sort of run the vacuum so that air is slowly being sucked out here. So if Boyle's law is to be true, so the air molecules around us, of course, exert pressure on us everywhere. But in this vacuum here, we're taking away the air. So here we have less and less air molecules that are exerting pressure on the gas inside the balloon. And as a result, we can see here a dramatic change in the volume. The pressure is getting low. No, the pressure around the balloon, because it's the pressure of the gas molecules inside the chamber surrounding the balloon that's sort of exerting the pressure in the balloon. The pressure inside the balloon would also technically decrease, because then the volume of the balloon has increased, but the number of molecules inside the balloon is still the same. But there's now a bigger volume for them to move around, so they hit the walls of the balloon with less frequency. So also the and if we open this, I'm now letting some air in, slowly letting air in. So as I open this valve, so air is now entering the chamber, and I guess I opened it so quickly, and so there was this sudden rush of air going in, which compressed the balloon so quickly that it popped. But in principle, anything we have to wait for this open up like this. Right, so in principle, if you put anything there with a lot of gases, like marshmallow with a lot of air pockets in there, you want to see what will happen if we make this into that. after this experiment, there's probably enough for everyone to share. There's something. Will probably take a little bit of time. We'll leave the marshmallows there for it will take a little bit of time. Something happened. Something changed. We did this and it worked great. So unless I messed up the vacuum chamber. I think now air is coming in. Oh, now there. The other valve, other way. You see? Are they changing? This is the reference. Yes, it's working. I don't know if it can feel. I mean, we never left it long enough to see if how big they can get before they pop. Because eventually, right, all materials that experience stress, they will eventually reach their elastic limit, which will cause them to break. So I think eventually these marshmallows, the air pockets will eventually break, and they will cease to expand some more. But then, yeah, right. Oh, interesting. So, so the only reason they're popping up is the gas trapped inside it. It's expanding, right? So if you put something there with, like, if you try to put cotton, which is the gas is not contained, it doesn't really blow up. If you put something that's quite compact, yeah, it's also, they probably expand, but not as much as if you put something with a lot of air, like the balloon that we did earlier. But yeah, so I think we can stop this. They've blown up quite a bit. And so, yes, so Boyle's law, as we've seen here, and that's your reference marshmallow there, increase the pressure, increasing or decreasing the pressure results to an increase in the volume. The gas expands if you increase the pressure. Of course, if you let air in, what will happen if you let air in? And if you increase the pressure, the volume decreases. And have you ever been to the cafe and order like a flat white, and they give you like this tiny hard marshmallow that sort of looks something like this? So yeah, so there you go. All right, so this is a macroscopic description of what's happening, because we can observe it with our eye. We can observe how the volume of the marshmallow or the balloon changed. So these are macroscopic descriptions, just like, you know, when we learn about temperature and temperature, we said that if the temperature increases, then the object expands. We looked first at the expansion of solids and liquids when we first learned about temperature. And yesterday we saw that temperature also affects gases. Right, and so I'll do this demonstration again because it's cool. I brought again liquid nitrogen, -200 degrees Celsius. And I have this balloon dog that's filled with gas, of course. And if Charles' law was true, Charles' law says that the volume of the gas inside this balloon is proportional to its temperature. So as the temperature of the gases inside the balloons decreases, then the volume of the balloon will also decrease. Right? And if I take out the balloon, which I would expect it will now be disfigured, right? So you are essentially increasing the temperature of the gases inside once again, and you are able to resurrect the balloon, except that, resurrect the dog, except that it's now popped. Again, once materials reach their elastic limit, they break. And so increasing the temperature so much will, as you increase the temperature, the volume increases as well. And if again if the balloon reaches its elastic limit, that's when it breaks. So this is again a macroscopic description of temperature because we can observe it with our eyes, right? The expansion, the actual expansion or contraction of gases and objects can be observed by the eye, but so they are macroscopic descriptions. When we say microscopic, then we're looking at what's happening to the atoms in the material or the gas particles that make up the gas. So let's now look at how we describe microscopically the change in the particles making up the gas. So microscopically, we say that the higher the temperature, the greater the translational kinetic energy of the particle is, meaning, right, as you heat up the gas, increasing its temperature, then the gas molecules start to vibrate, and so they move. And the more heat energy you give them, the higher their temperature becomes, and the faster they move. Okay, so it's the same case for solids, liquids, and gases. Okay. Solids, liquids, and gases, the atoms that make up the material, they vibrate and move as you increase their temperature. But for this lecture, we will talk mostly about gases. Okay. Right? So the kinetic theory of gases tries to connect the macroscopic picture with the microscopic picture. So it establishes this relationship between what's happening to the atoms or the gas particles that make up the material to what we observe in terms of the expanding of the gas or the increase in the gas temperature. So microscopically, if we want to describe what's happening to the gas particles, we need to state the actual position of the particles at any given time and the speed of the particles at any given time in relation to what's happening to the pressure, volume, and temperature. But as you can imagine, the gas particles, they're moving randomly. So it's very difficult to specifically pinpoint where the gas particle is at any particular time. And it's also difficult to determine the specific speed of each individual particle, especially if there are a lot of gas particles. So for kinetic theory to reconcile the microscopic and macroscopic picture, it needs to make some assumptions to make the analysis easier. So here I list down the assumptions for kinetic theory, and based on these assumptions, we are able to derive a relationship between temperature and the kinetic energy of the gases. Some notable, so you can just read through these slides. I mean, I don't need to read through them. Just some notable assumptions here. When the gas particles collide, they collide perfectly inelastically, meaning kinetic energy is conserved. And in that case, and that the when they collide, they obey Newton's laws of motion, so that one particle exerts force on the other, and the other particle exerts force on the other particles. So using these assumptions for the kinetic theory, we can relate the temperature of the gas to the average kinetic energy of the gas particles that make up the gaseous system. Okay, so if you're this equation here, according to kinetic theory, says that the temperature of the gas is proportional to the average kinetic. So this is the average kinetic energy of the gas particles that are randomly moving inside the container. So if you're interested on how this equation was derived specifically, I will not discuss the specific derivation of how we arrive at this equation. I will direct you to the textbook to see if you're interested in seeing how this equation was derived specifically. So in this lecture, we'll focus more on interpreting these equations that was derived by the kinetic theory. So this bar, of course, we use K as the symbol for kinetic energy. Okay, so the bar above the kinetic energy symbol means average. So we're getting the average kinetic energy because you have many gas particles. For example, inside this balloon, you have many gas particles, right? And they're moving randomly inside with various speeds. So each gas particle will have its own kinetic energy. So this bar here means that it's the average kinetic energy of all the gas particles inside this balloon that is proportional to the temperature of the gas, the overall temperature of the gas inside this balloon. Right, so K is just a constant called the Boltzmann's constant, which we've encountered yesterday. Right, developing this relationship further, we learned that kinetic energy is the energy of objects that are moving. So the definition of kinetic energy, so compare that to K is equal to 1/2 mv squared, which was the definition for kinetic energy we learned when we learned mechanics. So if we're getting now the average kinetic energy, then the average kinetic energy will be proportional to how fast the particles are moving on average. So average kinetic energy is how fast the gas particles are moving on the average. Okay. So I avoid here to say that it's proportional to the average speed of the particles, because if something's moving randomly, the average is not really representative of v squared. This is v squared and then get the average, right? So it's not really the average speed as we know average speed to be. And we'll talk more about that later on. But for now, let's just say that we know from definition, the kinetic energy is 1/2 mv², and therefore the average kinetic energy will be 1/2 mv² average. This term here, v² average, being how fast the molecules are moving on the average. Right, so these two equations, they both contain average kinetic energy. So therefore we can equate those two. We can therefore now directly relate the temperature to how fast the gas particles are moving on the average. Okay. Right, so I've been saying all along that the higher the temperature, the faster the gas particles move, right? But this equation derived by the kinetic theory of gases gives us a concrete definition, a concrete equation that shows us directly that the temperature is proportional to how fast the gas particles are moving, so that the higher the temperature, the faster the gas particles are moving. Okay, so just to summarize, the average kinetic energy of the molecules, it's equal to 1/2 mv² average. It's also equal to 3/2 kT. The first one, this is from definition, the definition of kinetic energy, 3/2 kT. This is what's derived from the kinetic theory of gases. So this is the average kinetic energy of one molecule. So if your balloon is made up of n molecules, therefore the total kinetic energy will be n times the kinetic energy of one molecule, where n is the number of molecules in the gas. Right, so are we okay so far? So far we've just seen this equation that directly relates the temperature to the speed of the particles inside a balloon, for example. All right, so now let's deal with this mv². What is this what is this v² average? And how do we calculate for this? So as I've mentioned earlier, the average, so inside this balloon, you have many gas molecules or gas particles, and they're moving randomly. Anything that's moving randomly, if you get the average velocity of that, the average velocity is 0, right? Because each one of them have random directions. So if you add up all the directions to the left, to the right, up and down, they will end up to have an average of 0. So it's not really useful to get the average velocity of the particles in the gas. And likewise, it's not really useful to get the average speed of the particles. And so instead of getting the average speed or average velocity, we define what we call root mean square speed, or VRMS speed, or RMS speed. And the RMS, or root mean square speed, is how fast the molecules are moving on the average. Slightly different way of saying it, but it means average speed and how fast they are moving on the average mean different things. Okay. So average speed, this is how you calculate the average speed, the usual way. Add up all the speeds and divide it with the number of gas molecules. Whereas for the root mean square speed, or how fast the molecules are moving on the average, you first have to get the square of the speed. then get the average, then get the square root. And that's why it's called root mean square. You square first, meaning exponent 2. You square it first, and then you get the average, which is the mean or average, and then you get the square root. Right, so mathematically, it's shown like this here. Right. And RMS speed is related to 3 kT over m. This one, of course, came from this one. 1/2 mv squared average is equal to 3/2 kT. Okay, half will cancel each other out, and so v squared average is equal to 3 kT over m. So v squared average or v squared mean is equal to 3 kT over m. And if you get the square root of this, that is where you have the definition for RMS speed, square root of 3 kT over m. All right. Okay, let's do some practice. You have a group of 10 identical monatomic molecules. Monatomic meaning mono meaning single or one, and atomic atom. So these molecules, they're made out of a single atom. So for example, oxygen or nitrogen. So you have 10 of these monatomic molecules, and they have the following speeds. One molecule has a speed of 10 meters per second. 2 molecules has a speed of 15 meters per second. 3 have a speed of 20 meters per second, and 4 have a speed of 25 meters per second, for a total of 10 molecules overall. And we're given the mass of each molecule. Okay, calculate the mean or average speed. How is that different to the RMS or the root mean square speed? And then from there, calculate the average kinetic energy and the temperature of the molecules. I don't know if there are scientific calculators yet who can calculate RMS, like how you input how you can input the speeds and just click at a single button RMS. Are there? Okay. Yeah. You're welcome to use that function, by the way. All right, so mean or average speed is the usual way we calculate average. So nothing special about that or nothing different. Simply add up all the speeds. Remember that there are two, for example, there are 2 molecules with a speed of 15 meters per second. Right, so hence this 2 times 15, 3 molecules with 20 meters per second, and 4 molecules with 25 meters per second. So, so nothing special, nothing different with getting the average speed from what we know from before. So for RMS speed is defined as this square root of v squared average. So yeah, if you don't have one of these fancy calculators, this is how you calculate RMS speed. So first, you need to work from inside going out. So you need to do the square first. You square the speeds. Okay. And then after squaring the speeds, you get the average of the squared speeds. Okay. Again, getting the average is the usual way we get the average. You add up all the speeds, divide by the number of molecules, except this time you're getting the average of the speeds squared. So don't forget to square each of the speeds before getting the average. Then once you've obtained the average of the squared speeds, you get the square root, so square root of 425, which is 20.6. Right. Cool. Relatively straightforward, I hope. Yeah. It's just applying the definition of RMS. Yeah, you work this equation out from inside going out. So you start with square, then average, then square root. Once you have the RMS speed, you can then calculate the average kinetic energy of the molecules, because the kinetic and average kinetic energy is 1/2 mv squared average. So we're getting the average of the squared speeds. Right. The RMS speed is defined as the square root of v squared average. So to find v squared average to use in the equation of kinetic energy, you then have to square the RMS speed. Okay. Right. Does that make sense? Why you have to square the RMS speed in order to get this v squared average? Because RMS speed is defined as square root of v squared average. You just want v squared average in the kinetic energy equation. So you have to get rid of the square root. You get rid of the square root by squaring the VRMS. Okay. Cool. Right. So average kinetic energy is 1/2 times the mass. The mass is given 2.9 times 10 to the -5, but there are 10 molecules. So 10 molecules. Okay. Each molecule has a mass of 2.9 times 10 to the -5. So don't forget to multiply with 10 and then multiply with v squared average, which is now your VRMS squared. So don't forget to square the VRMS. Okay. Giving you the correct kinetic energy, of course, in joules. All right. Okay. All right, so it's relatively straightforward, but it's easy to miss things like doing the square or doing the multiplication. So just be a bit conscious about these things when you do your calculations. So next, we want to find the temperature of the molecules. So what we know so far is the RMS speed and the kinetic energy. We know that the temperature is related to the speed v squared average, and also related to the kinetic energy via the kinetic theory of gases. Right, this is the direct definition from kinetic theory of gases that relates the temperature to the average kinetic energy. We've solved for the average kinetic energy. Small k is a constant, the Boltzmann constant. and therefore we're able to find the temperature of the gases, knowing the average kinetic energy. All right, are we happy with this example, how we solve for especially distinguishing average speed and RMS speed and getting the kinetic energy, average kinetic energy and temperature from there? Okay, good. All right, so let's look at this other example, which will use the kinetic theory of gases in a different way as the previous example. Say in a sunny day where the air outside is 28 degrees Celsius. So we'll assume that the gas particles making up the air is also at a temperature of 28 degrees Celsius. The gas particles being, or gas molecules being, nitrogen and oxygen. Nitrogen has a mass of 28.02 U. Recall yesterday we learned about atomic mass unit U, which is the non-SI unit for mass. And for oxygen molecules collectively, they have a mass of 31.98 U. And we want to find the RMS speeds of the nitrogen and oxygen molecules in the air. So how fast are the nitrogen and oxygen molecules moving on the average at a temperature of 28 degrees Celsius? Right, from definition, RMS speed is defined as this. It's either getting the square, average, and square root of individual speeds of the individual molecules. But in this case, we're not really given the individual speeds of the nitrogen and oxygen molecules making up the air. So this definition of the RMS speed will not be useful, but we do have a relationship that relates the temperature of the molecules to the RMS speed via the kinetic theory of gases. So we know the temperature of the air, which we'll assume to be the temperature of the nitrogen and oxygen molecules as well. The only other thing we need here is the Boltzmann constant K and the mass. So we need to figure out then the mass of the nitrogen and oxygen molecules. They're given in atomic mass units U, but we need to determine their mass in kilograms. Okay. Kilograms is the SI unit for mass. We've seen this conversion factor between the atomic mass unit U and kilograms, so we need to use that to convert. It's essentially a conversion problem, right? Converting 28.02 U to kilograms. 1 U is equal to 1.66 times 10 to the minus 27 kilograms, and hence doing this conversion gives us the mass of nitrogen 4.65 times 10 to the minus 26 in kilograms. And you do the same thing for oxygen. The mass of oxygen molecules collectively is given in atomic mass units U. It's again a conversion problem between atomic mass units U to kilograms. So multiplying the U with the conversion factor gives you the mass in kilograms. Right. That then provides us everything we need to solve for the RMS speed. Okay. So for the nitrogen molecules, the RMS speed is 580 meters per second. Okay. You have 3 volts times the Boltzmann constant times the temperature. Okay. Don't forget to convert your temperatures to Kelvin. It's necessary to convert your temperatures to Kelvin because the Boltzmann constant K is given in kelvins. Okay, so you cannot get away from not converting Celsius to Kelvin. Divided by the mass of the nitrogen molecules. And sorry for the typo, this is an exponent minus 26. It's a superscript. And you can do the same thing for the oxygen molecules to get the RMS speed of the oxygen molecules. All right. Cool. Are we happy with the solution to this problem, or are there any questions? We're good.
So it's saying that helium molecules travel slow.
Yeah, if you think about it, it sort of makes sense. Yeah. They need more energy to go faster. So, right. So, so we said that the molecules, they're moving randomly about, and each one will have their own speed. It's not necessary that they have all the same speeds, as we've seen in this example. Nitrogen and oxygen molecules, they have different RMS speeds, and individual oxygen and individual nitrogen molecules will have their own speeds anyway. So the Maxwell distribution, which is given by this equation here, and we don't have to derive this equation, nor do we need to think about this equation so much. It's just an equation that gives us the f of v is the relative number of molecules, which is on the y-axis here. It's the relative. It gives us a distribution of the speeds of the molecules in the gas. So if we make a graph, if we do a simulation and put different speeds for each of the gas molecules, we will be able to solve this function f of v. And if we make a graph, the graph will look like this. So it gives us a distribution of the different speeds of the particles or molecules making up the gas system. So we can define different parameters here. VMP, this is the most probable speed. As you can see, it's here. It's at the peak. That means it's the most number of molecules will have, this particular speeds. The x-axis is speed, y-axis is the number of molecules. So this peak here, the VMP, means you have the maximum number of molecules having this particular speed. V average is around here. It's how we calculated the average earlier, right? Add up all the speeds and divide them by the number of molecules. In relation to temperature, the average speed is can be calculated using this equation. Okay. And for the RMS speed, it tells us you can pick up from this graph here the number of molecules whose speed is equal to the RMS speed, and RMS speed is calculated as we've seen earlier from this equation here. So the Boltzmann distribution is simply a graph where you can pick up from the graph 3 points to tell you how many molecules have a speed equal to the most probable speed, how many molecules have a speed equal to the average speed, and how many molecules have a speed equal to the RMS speed. If we change the temperature of the gas, if we increase the temperature, for example, from 300 Kelvin to 900 Kelvin, the Maxwell distribution also shows us how the most probable speed changes, most probable speed, average speed, and RMS speed changes. And only the key idea here is that if you increase the temperature, the most probable speed will shift to higher speed. So remember, x-axis is speed. So this means slow. Well, 0 is at rest. And you're going from slow speed to fast speed. So if you increase the temperature from 300 Kelvin to 900 Kelvin, notice how the speed shifts so that the more and more particles will move faster as you as you increase the temperature. More and more particles will move faster, and therefore the number of particles having the most probable speeds will shift towards higher speeds. Does that make sense? Yeah.
Why does the speed increase to a point as the number of molecules increases?
This one. No, it's just saying that there are more. So number of molecules means there are more molecules having this fast speed. So if you increase the temperature, then all of the molecule speed will increase in general, but this one tells you that more particles will have this maximum speed. Yeah. Okay. All right, so what we've learned so far, average, kinetic theory of gases relates the temperature to the average kinetic energy of the gas. And we said that this is for one molecule. So if you have n molecules, then the total kinetic energy will be n times the kinetic energy of one molecule. So n will be the total, the number of molecules of gases in the system. So this allows us to define what we call internal energy. So internal energy is the total energy of all the molecules in the object. For gases, so we've learned before, energy consists of kinetic energy and potential energy, right? But for gases, for ideal gases, we assume that the potential energy is negligible, and that's a consequence of the assumption of the kinetic theory of gases, where the molecules are spaced far apart so that they only have kinetic energy, and their potential energy is negligible. So as a result of that assumption, the internal energy, or the total of all the energies of the molecules in the object, will therefore be equal to the total kinetic energy, the number of molecules n times the average kinetic energy of each molecule. Right, and since we've already derived this relationship between average kinetic energy and temperature, the internal energy, or the total energy of the molecules in the objects, which we call internal energy, will then be equal to the total kinetic energy of the gases, which is a consequence of assuming that only kinetic energy is present and potential energy is negligible. Okay. Right, so n is the number of molecules. Okay. We can use the definitions we learned yesterday and rewrite that equation in terms of the number of moles and the universal gas constant R, but these two equations are equivalent, and which equation to use just depends on whether you know the number of molecules or the number of moles making up the gas. Okay. So in the coming lectures, we will talk more about internal energy. But yeah, this slide just summarizes the variables. But now let's just, this slide just distinguishes the definition between temperature is just the average kinetic energy of a molecule, whereas internal energy takes into account the total energy of all the molecules. So if you compare these two equations, they're similar except for the internal energy accounting for the number of molecules because you want the total energy. Okay. Right, so just a little conceptual exercise before we end. We have here 3 scenarios. We're comparing 2 gases, and we want to find which gas has a greater internal energy. We assume that if the gas has a bigger volume, that means that there are more gas molecules. It's not necessarily the case. Because 3 molecules can occupy this room at the same time as 1 million molecules can occupy the same volume of room. But for the sake of this exercise, we assume that a bigger volume means more gas molecules. So for the first case, you have 0.5 liters of air at 30 degrees Celsius, and comparing that to a bigger volume, 1 liter of air at the same temperature, which gas will have a greater internal energy. Yeah, more air means more internal energy. Yeah, and it's the number of molecules. So of course, given the same temperature, more air will have. How about the second one? 1 liter of air at 10 degrees Celsius, and then the same volume, 1 liter of air, but at a higher temperature. Which one will have a greater? Yeah, good. So higher temperature, of course, will have higher internal energy. What if you have 2 different volumes and 2 different temperatures? 0.2 liters of air at 25 degrees Celsius versus 0.05 liters of air at 30 degrees Celsius. Which one will have a higher internal energy? Yeah, well, plug it into the equation, but essentially it's the number of molecules times temperature, right? So you need to figure out whether 0.2 times 25 is greater or less than 0.05 times 30. It's a combination of the number of molecules times the temperature. Yeah. And loosely, we assume that the volume is proportional to the number of molecules. So this one, 0.2 liters at 25 degrees Celsius will have a higher internal energy. Good. Right, so we've defined internal energy. In the next lecture, we will look at the transfer of internal energy and talk about calorimetry and heat transfer. But if there are no questions, then we can end our lecture. And I wish you a good day. Hopefully the sun will come out soon. It's been peaking intermittently this morning, but I'll see you in the workshop tomorrow.
Questions about the, this week I've already done the tests, so like